Hello, I am Jacob from Intrepid Protoworks, and today we're going to go over the One Way ANOVA. This is a follow-up to our video on the F distribution, the One Way ANOVA will be our first application of the use of the one-way distribution. We'll start off with some imports. We'll import from math, we'll import gamma, we'll import decimal, and we'll import CSV. Then for decimal, we will go ahead and set context to 100 significant figures. And then same as the video where we covered the F distribution, we are going to go ahead and do the F probability distribution function. It'll take 3 arguments, F, degrees of freedom 1, and degrees of freedom 2. And now, for the sake of ease of calculation, ease of tracking, we're breaking up the different parts of that function. If you want more details on the function, take a look at our last video. We're going to break it up into different easy to calculate parts. The top and bottom, which are then made into our numerator, A and B, which are then plugged into a calculation of beta using the gamma function, and our denominator, which is just F times beta. Once we have that, we can return our PDF function, and then that'll allow us to take the next step, which will be from P, get P from F, and it'll also take F, degrees of freedom 1, and degrees of freedom 2. We're going to go ahead and add, real quickly, we added in import sci-fi.integrate up at the top. Now this is again the same as our last video. Probability and error equals sci-fi.integrate.quad. It'll take a probability distribution function, and it'll go from 0 to F, and it'll also take 2 additional arguments, which is df1 and df2, and that'll return probability. And then we'll just go ahead and add in a mean function real quick. This is again the same as almost every other video that we've done where we use this. Now with all of this in place, we are ready to calculate our F ratio. So we'll go ahead and make our next function, which is calculate F. It'll take factor. The ANOVA takes a factor or factors rather than like a variable, or they're the same thing basically, but it's nomenclature within statistics. So the first step is to open up a list, call it means, and then we'll take our group size, which will be the length of our factor, and then for level in factor, our mean will get the mean of that level. So our factor will be a series of lists, one for each level of our factor in this case. There are other ways to do this. You could arguably use a Python dictionary for this, or a pandas data frame, but we're going to just stick with using a list because it's simple, easy to understand for somebody who is not very familiar with Python. So for level and factor, our mean will be get mean for that level. And then to our means list, we'll append that mean. Then our overall mean will be the mean of all of our means. That's a very meaningful statement. Between groups, sum of squares, we'll set that equal to 0. And then for mean and means, we'll calculate a deviation score. That'll be our group size times our mean minus our overall mean taken to squared. And then we will add that to our between groups sum of squares. Add some space there for formatting. Next, we'll set our number of groups. We'll set that to the length of our factor. So this is the number of levels in our factor. And now we will calculate the between groups degrees of freedom. The between groups degrees of freedom will be equal to the number of groups minus 1. So that's pretty simple. Now the between groups mean square will be equal to the between groups sum of squares divided by the between groups degrees of freedom. Now we need to calculate the second part of our F ratio. This will be the within groups mean square, and we'll start off by setting the within groups mean square equal to 0. So to calculate the sum of squares for the within groups, we need to do for mean, level in zip means and our factor. This will let us go through every value in our data set for every level and compare that to the mean. So deviation score equals value minus mean within groups mean square plus equals our deviation square squared, or deviation score squared, and then our within groups degrees of freedom equals the number of groups times the group size minus 1. So this is a little bit more complicated of a for loop. So again, we're going through mean and level in the first part of our loop, and then we zip together means and factors, so we loop through those at the same time. And then for each value in the level, we take the mean of that and go through it. There should be the same number of levels in the factor as there are means. And with all of that, we can finally do the F ratio. So the F ratio is defined as the between groups mean square divided by the within groups mean square. And there's an error that we missed earlier. We defined the within groups mean square rather than within groups sum of squares. All that is left is to return some values. So we're going to obviously return our F, and then we're also going to return our between groups mean square and our within groups mean square. The reason we're doing this is sometimes people want to see it, so we're just going to go ahead and bring it along for the ride in case we want it later. Looks like we have several typos to fix. So between groups sum of squares, between groups sum of squares, let's fix that. And then we have one more between groups mean square and between groups sum of squares. All right, so that is all the typos. So now we can get a p-value from an f-value with the probability distribution function. We can get our f-value itself. Let's go ahead and do our one-way ANOVA. So we'll define that, and I'll take a factor and an alpha level. Make ourselves some space, and we'll go ahead and set a value called, or a variable called significance. We'll set the value of that variable to false. And then we'll get our f, our between groups mean square, and within groups mean square from our calculate f function, and we'll put in our factor for that function. Then we'll calculate our degrees of freedom between, but to that do the length of our factor, -1. And we'll do our degrees of freedom within, and to calculate that, do the length of our factor times the length of the level of a factor -1. And then because we can end up with some math overflow errors, there's ways around this, but for now we're just going to kind of shortcut it. We'll say define within degrees of freedom within used equals degrees of freedom within, and if degrees of freedom within used is equal to 300, we're going to go ahead and print off a warning, do a new line so that warning stands out, and set our degrees of freedom within used equal to 300. The reason we're doing this new variable is so that we can report the original degrees of freedom in addition to printing off the warning. And then we'll set our p equal to get p from f, and that will take our f, our degrees of freedom within, and our degrees of freedom used. Fix a quick typo up there, we want to do less than or equal to. And then if p is less than 1 minus alpha, or if p is greater than 1 minus alpha, then we will set significant to true. Now that is basically our ANOVA, fix a typo. And now we'll go ahead and return our p-value. We'll round that to 7 decimal places. We'll return our f ratio, round that to 4 decimal places. And then we'll return significant. And then we're going to return the 2 degrees of freedom, because usually when you're reporting an ANOVA, you want to report degrees of freedom for it. So for our example today, we're going to go look at all of the different races reported in this data set we have. We're going to open up a new list for one. We're going to go ahead and put as a comment the value that is coded as. If you're curious as to where this information is coming from, if you look back at it earlier in the series, this is from the IPUMS database, and this is what is included in the race variable for that database. Some important things to note about a one-way ANOVA: it will not tell us which of these are significantly different from what other parts. It'll just look at all of the levels. So we're saying that this is the race variable, and that each of these races is a level of this variable. And it'll just tell us that somewhere in that mix, there is a statistically significant difference. We're not going to carry any further that in this video. That will be for 2 videos down the line when we do the videos starting to go over post-hoc tests. Our next video will go over another statistical distribution needed to use the Tukey on a significantly different test. For this, we're just doing a one-way ANOVA. looking at the variable, all the levels of the variable of race. What we've been doing here while I've been talking is we've opened up our data file, and we've seen this in basically every example. So we go through, we filter out the header, we filter out non-applicable replies, we filter out minors, we filter out people who didn't earn an income, and then we go ahead and sort each of the people in this 3 million sized data set into each of their race lists. So we'll say like if row 2, which is the row for race, is equal to 1, we will append that person's income to a list of the white incomes. Then we'll say elif if it equals 2, we'll append it to black, and we'll continue that all the way down until we've gone through all 9 of our race categories. And then we'll go ahead and copy and paste the elif statements because they're basically the same other than the list that they're being applied to and the numbers associated. We'll paste all those in, and then we'll change through the numbers, and we'll change through the lists associated with each. I'll go ahead and speed through the rest of this. Once we have all these lists changed to their appropriate names, we'll go ahead and check over everything. This is a area that's ripe for typos. Looks like we missed putting in the empty list for other race up top. So go ahead and add that in real quick and fix that. And again, this could probably be done a little bit more efficiently using a Python list. There's also other really good statistical tools, but the point of this series is to keep as few modules getting involved as possible. So, and especially modules that might require an install. So we're going to go ahead and import random. And then we'll go ahead and set sample size equal to 100. And then we'll go ahead and do white sample, which equals random.sample. And it'll take our list for white and our sample size. Then we'll go ahead and repeat this process for all the other race variables. Now that we have all of our samples, again, we're taking samples for the sake of the example. We realize that the data set's much bigger, and in normal circumstances, you want to use everything you had. But for the sake of our example, we're just going to assume a sample size of 100 in this case. So now with all the samples, we're going to go ahead and define a race factor. We'll set equal to an empty list, and then we will append each of our samples to that. So to do that, we'll just do race factor.append white sample and then black sample and all the way through the rest of our samples. And again, using lists is a little bit of a cumbersome way to do it, but we want to stick with it for now for simplicity's sake. I'll think about doing dictionaries later on. So we're going to go ahead and set our alpha to 0.05, and we're also going to not forget to append our other race sample as well. I don't know why I keep on forgetting that one. Make ourselves some more space, and we are ready to do the ANOVA. So we'll define P, F, significance, degrees of freedom between, and degrees of freedom within is equal to a one-way ANOVA. That will take our race factor and our alpha. Now we'll say if that is significant, we will go ahead and do a print statement. We're going to go ahead and switch over to doing something a little bit better for reporting. And we'll also do the ad hoc tests in a future video. So we're going to do something that's a little bit closer to what you would see in like an APA format. I'm not really wanting to do APA format, but it might be better just to get a little bit over to that. So we'll type out there were, if significance is true, so if there were statistically significant differences between group means as determined by a one-way ANOVA with degrees of freedom such and such and f of such and such equals f of such and such, giving us a p of such and such. Looks like we have a syntax error. Looking through real quick, checking for any commas I've missed. And there it is. We missed a comma right there. All right, so we're going to copy and paste this, and then there were no statistically significant differences. If there aren't any statistically different differences, you don't need to do post hoc tests. Looks like I misspelled scipy.integrate, so we'll go ahead and just not mess with that and copy and paste over the correct spelling. Try running that again. Looks like there is an error with opening our CSV file. So I'll go down to that. And it looks like we forgot a 0. Save and run one more time. So we did not get anything, if not significant. So fix that typo one more time. And there are no statistically, so this is possible with a random sample that you can end up, it should be probably somewhere in the ballpark of a 1 in 100 chance. So check one more time to see if that wasn't an aberrant thing. No, it's still giving us, so more than likely up above we have put something in wrong. So we will go ahead and go up and take a look at our One Way ANOVA. See if there's any issues in there with the way we're calculating our p-value. I'm not seeing anything. Next, I'll go ahead and check through, make sure that we're not accidentally appending the wrong things or putting the wrong parts into our list of lists. Now let's go up and calculate our F. Take a look at this. Looking for any typos, I'm going to go ahead and look over at my notes real quick to make sure I'm not making a mistake. So now I'm going to just go ahead and copy and paste from my notes and then undo and redo and look for differences I've made. All right, so I found one difference. Looks like I need to put a 0 in there. That should be the main difference there. There's some variable name differences, but I made that consistent going through, so that shouldn't be an issue. All right, there we go. And run that again. The worst is P is really small. We're very confident in that finding. P is even smaller. Yes, that's smaller than 6 zeros on 1. And yeah, so that should be about it. Thank you for watching. In our next video, we'll go over the statistical distribution that will be needed for the Tukey honestly significant difference post hoc test. And we'll probably do that and maybe one other post hoc test for now. And then after that, we will go into the two-way ANOVA. Thank you for watching. Don't forget to like and subscribe. And if you have any questions or comments, put them down below.